Let's see how quickly we can go through everything you need to know for GCSE Maths. There isn't a lot of difference between the boards, so this should be useful no matter which you do. Let's go. Ordering values or numbers into a list when they're all jumbled up merely requires you to work through from the largest part of the numbers, that's tens of thousands in this case, then work down through to the thousands, hundreds, tens, units, until you've ordered them from smallest to largest or vice versa. You deal with decimals in the same way, it's just that we go into tenths, hundredths, thousandths, etc. Ordering fractions is a bit trickier, as it can often require you to do so for those with different denominators, the number on the bottom. For example, which is bigger, 5/6 or 14/18? To make them have the same denominator, you multiply the top and the bottom of one or both of the fractions. It should be fairly obvious that 3 lots of 6 go into 18, that is 18 is a multiple of 6, so we can multiply the 5 and 6 by 3 to give 15/18. So that means it turns out that 5/6 was the larger fraction after all. What about 2/3 and 6/8 though? 3 doesn't go into 8 nicely, so we can multiply both by the other's denominator. Multiply the top and the bottom of 2/3 by 8 and we get 16/24. 6 and 8 times 3 gives 18/24, so 6/8 is the larger fraction here. The equal symbol shows that an unknown value or an expression with one in is the same as another. Inequality symbols show that one number or an unknown value or number is not equal to another. These arrows show if one is larger or smaller than another. Simple with numbers, but if we replace with a symbol like x, that means whatever number y is, it must be bigger than 5, and it cannot be 5. A line underneath means equal to or greater than, so it could also be 5 now. An interval is when a value can be between two numbers. But to do this properly, one of the symbols must be or equal to as well to make sure that intervals don't overlap. Estimating or approximating is useful when you need a quick answer that doesn't have to be exactly right, say when estimating how much gravel you need to buy in order to cover an area. We can round the numbers involved to one significant figure, or sig fig, or SF for short, to allow us to do a mental calculation quickly. What's 32 times 68? Well, let's round them to 30 and 70. Multiply the first sig fig, which gives us 21, and then we have the 10 times 10 too, which is 100. 21 lots of 100 is 2,100. We use a wavy equal sign to show that 32 times 68 is approximately 2,100. To truncate something is to make it shorter. Every measurement you make, say with a ruler to get length or balance to get mass, always involves some rounding. In science, we say the resolution of a ruler is 1 centimeter if there's a line every centimeter. So you can't make the measurement 8.5 centimeters, say, only 8 or 9. But that means that a measurement of 8 centimeters has an error interval of 0.5 centimeters. The value could be anywhere between 7.5 and 8.5 centimeters. Incidentally, in science, this idea is called the uncertainty in a measurement or value instead, because it's done better there than it is in maths as per usual. But in maths, we say that the error interval is always half the accuracy of the measurement, or half the resolution. So if a mass is measured to the nearest 10 grams, say, the error interval will be 5 grams. Going 5 grams either side of any of these masses measured will give us those upper and lower bounds. These of course are just for non-calculator papers. To add numbers, place them on top of each other, it doesn't matter which one's on top. Start on the right and carrying the number of tens to the next column. Add the tens, carry the hundreds, and so on. To subtract numbers, it does matter which one is on top. Again, start on the right, and if the top number is smaller than the bottom, you carry a 1 from the next column. Multiplying, you have the grid method, whereby you give the hundreds, tens, units their own column and row. Do these individual multiplications and write the answer in each box, then add up the total. To do short division, you put the number you're dividing in the box and the number you're dividing by outside on the left. Start on the left by dividing each digit, carrying whatever remains over to the next digit. If the digit is smaller than what you're dividing by, just carry it over straight away. You'll often end up with a remainder at the end. This remainder can be given as a fraction of the number that you're dividing by. If you add a negative number, that's the same as subtracting the positive version of that number. Now, I'm old school, so I'm still in the habit of calling negative numbers minus numbers, which I'm sure many people will tell me off for, even though it's something that's only become fashionable over the last few years. Of course, you'll never have to write the actual word, just the symbol, so it doesn't really matter, but just so you know. Subtracting a negative number is the same as adding the positive value, so 5 minus negative 3 equals 8. The minuses or negatives cancel each other out. It's similar when multiplying or dividing negative numbers too. Multiply a positive number by a negative number and the answer must be negative. If they're both negative, the answer must be positive, as the negatives cancel. Incidentally, this is why the square root of 25 is 5, but it's also minus 5 too. This is why the quadratic formula is a thing. It gives both possible solutions to a problem that has a squared number in. BIDMAS or BODMAS, this refers to the order that you must do operations in, that is plus, minus, times, divide, when you have a combination of them in a calculation. It goes in this order: brackets, powers or indices, divide and multiply, then add and subtract. If there's anything inside brackets, you always do that first. A power on a number is also called an index. The plural is indices. I much prefer using the word power, so that's what I'm going to be using from now on. If you have a power on a number, the O or I, you calculate that before doing anything else. We then have dm, do any multiplying or dividing, then finally carry out any adding or subtracting. Honestly, I kind of hate the concept of BIDMAS, as I think brackets are as important to the language of maths as punctuation is to English, so my advice is this: put brackets around multiplies or divides and you'll be fine. One more thing, if you have one calculation over another, you divide them right at the end. Converting between decimals, fractions and percentages can seem intimidating, but you just need to remember what the whole is for each. Let's take the decimal 0.6. As 1 is the whole, whereas 100% is a whole when it comes to percentages, to go from 1 to 100, we just multiply by 100. And so it's the same for 0.6. 0.6 times 100 equals 60, 60%. Of course, any decimal or percentage can be written as a fraction instead. 0.6 is by definition 6/10, so 6 over 10. Can this be simplified? Yes, both bits can be divided by 2, so 3 over 5 is the simplest form of this fraction. What about something like 64%? Because it's out of 100, the fraction version is 64 over 100. Again, this can be simplified. You can divide both bits by 4, so this is also 16 over 25. If you find 1/3 as a decimal, you'll end up with 0.3, remainder 3, and another remainder 3, and another. These 3's will go on forever. This is a recurring decimal. In science, you would just round this to say 0.33 and write it as that. But in maths, we show that we have a recurring decimal by putting a dot above the 3, showing the 3 repeats forever after that. Sometimes it's not just one digit that repeats, but a few of them. 0.647 with dots above the 4 and the 7 shows that the 4, 7 repeats ad infinitum. It's just the Latin way of saying infinitely. If there's 3 or more digits that repeat, we technically put the dots above the first and last bit of the pattern. So this would be 0.513513 forever. A reciprocal is just 1 divided by that number. The reciprocal of 2 is 1 divided by 2, so that's just a half. We can also say that this is the same as 2 to the power of minus 1, as any negative power means we're dividing by 2 that many times, as opposed to multiplying instead. Let's talk about finance. This is one section I'm really not going to rush. I think it's really important that you guys understand how finance and money work. The more you do, the better position you'll be in to look after your money when you leave school and get a job, regardless of what grade you get in your exams. Income is what we call all the money you earn. Usually we talk about income per month. Salary is the total amount of money you're paid in your job every year, before income tax is deducted. That's the money the government takes from what you earn. If you work for a company, this is taken from your paycheck before the money goes into your account. This is called PAYE, pay as you earn. This was me when I was a teacher in school and other jobs I did before that. A benefit to this is that you don't have to do any calculations to find out how much tax you have to pay, and because it's already gone before you get paid, you're not hit with a surprise tax bill when the financial year ends. That's the 5th of April every year in the UK. Whatever you're paid then as a result will often be called your take-home pay. If you're self-employed though, you basically run a one-man or one-woman business like I do now. You have income, but then you have to spend money on things too. We call those expenses. For example, me having to buy a new laptop to make these videos after my old one died, rip. Profit is income minus expenses. You then pay taxes on this profit. Businesses also have to pay taxes on any profits made. The rates of all types of taxes change over time and they're different in every country. Currently in the UK, you can earn up to £12,570 without paying any income tax. This is called your personal allowance. For every pound you earn over that, you pay 20% income tax. So if your salary or yearly profit being self-employed is £27,570, that means you're earning £15,000 over that personal allowance. You have to pay 20% of this amount as tax. So let's do the calculation. 15,000 times 0.2, that's 20% in decimal form because we can't just use percentages in calculations, that's equal to £3,000. So taking that away from the total income, you're left with £24,570. There are also higher tax rates too if you earn even more money. VAT, or Value Added Tax, was introduced in the UK in 1973. Not satisfied with taxing what people earned, the government also wanted to be paid every time somebody bought something. VAT varies on what you're buying, but it's usually 20% on most products and even fuel. If you go into the shop as a customer, a random member of the public, you'll likely pay whatever is on the sticker price. My laptop cost £800, so how much did the government get as VAT? A bit tricky this. That £800 is essentially 120% of the base price. I want to know what 20% is. So 800 divided by 120 gives us what 1% is. Times that by 20 and we get £133 and change. So in reality, I paid the shop £667 for the laptop, and £133 VAT on top of that goes to the government. When a business spends money, they pay the VAT, but then they get to claim it back at the end of the tax year. In other countries like the US, you'll find something similar, often just called a sales tax. But sometimes this isn't included in the sticker price of what you're buying, so you would have to calculate how much extra it'll cost you. Then again, you'll often now pay a service charge at a restaurant here in the UK, say 10% of the final bill. So the £22 burger I had the other day ended up costing me £24.20. You can calculate the extra by multiplying the base price by the 0.1, that's 10%, and adding that on. Or you can multiply £22 by 110%, 1.1 as a decimal. Not the cheapest burger I've ever had by a long shot. Personally, I'd much rather see hidden charges included in the menu prices, but people have differing strong opinions on this. Debit and credit are ideas that can be very confusing and can very easily cost you money if you're not in the know. To debit basically means to take money from somebody. So if you buy a football with a £10 note, the shop has debited you £10 on the spot. If you use a debit bank card, that amount will be taken off your balance. That's just how much money is in your account. If your balance goes below £0, we say your bank account is now in the red, so called because they used to use red ink for this when everything was written down by pen. You're overdrawn, you're now in your overdraft, and the bank will now charge you money for every day you're in the red. That is, unless you have an agreed overdraft with your bank, so you overdraw a bit without being charged, which is useful, say, if there's a surprise payment you have to make, like a bill that's paid automatically that you forgot about. Credit is the opposite of debit. It's someone giving you money instead, but this means you have to pay it back. If you pay for something with a credit card instead, the money doesn't come out of your bank account straight away, but rather the credit card company, it can also be a bank, lends you that money for a month. It's basically a card that creates a mini loan every time you use it. There will be a limit, say £3,000 a month. But no matter how little or much you spend up to that amount, if you don't pay it back at the end of the month, you're charged a percentage of that amount after that. If you don't pay it back and do the same thing next month, your debt starts to snowball. There are often other fees associated with credit cards too, like when you get cash out of a machine. So what's the benefit to them? Well, it's like having a large overdraft that, if you pay it off soon enough, you don't get charged. So say you've run out of money, but you need to buy something before you get paid that month, a credit card is useful then. They can also improve your credit score, a vague number that banks can see and decide whether or not they want to offer you a loan, depending on your history of paying back loans. I think it's a bit of smoke and mirrors, if you ask me, to get people to borrow more. Personally, I've never had a credit card as I like to keep things simple. At least that was the plan. A store card might sound like a nice thing to have, like a loyalty card at a coffee shop, but they're not the same thing. Get this into your head now. Store cards are credit cards. Let's say you have no money but really like a pair of jeans. Swipe the store-specific credit card and then you have a month to find the money to pay them back. When I was 18, I went into a clothes shop, let's call it Top Boy, and they asked me if I wanted a store card. I said yes, thinking I'd get every 5th t-shirt free or something. The two guys were weirdly excited about it. That's because they get paid commission every time they bamboozle an unwitting victim like me. They get loads of details off me, and by the time I realised what I'd done and tried to back out, they said, "Sorry mate, it's too late, you'll have to cancel it next week," which was an absolute lie. A similar concept is buy now, pay later. I'm sure you've seen this on adverts. You buy a sofa, then you find the money to pay the shop back later for this loan, usually with interest. Sometimes you'll see 0% interest. Great, right? Well, maybe, but that's usually just for a year. If you take longer than that to pay it off, the sofa can cost you quite a bit more. Similar with cars too. If you go to buy a car, they'll ask, will you be paying for it or will you be having finance? That just means a loan. There are all sorts of different loans, some you should steer clear of and some that are unavoidable. I'd argue in the middle of the two are student loans, a loan issued by the government to help you pay for university fees. It's a special loan as you only start paying it back once you make a certain amount of money when you get a job, and it's just taken out of your pay every month if you're not self-employed. Opinions are split on these. Some people say they don't notice the money coming out, while some rue the day they ever agreed to get one. There's a lot of that in the US at the moment, actually. I think it largely has a lot to do with whether or not the university degree was worth it. Being honest, it's worth remembering that universities are for-profit businesses, not like schools, and so will do everything to convince you that it's worth getting that piece of paper at the end. For some it is, for many it's not. I know quite a few people who did apprenticeships instead of going to university, and they ended up earning more money sooner and with no student loan compared to those who did go to university. I strongly advise you seriously consider which route is best for you. Don't fall into the trap of thinking that you must go to uni. You also have some sketchy predatory lenders that might give you a payday loan. Really struggling to pay your bills a week before you get paid? These geezers will loan you what you need at an APR of up to 1,500%. APR stands for annual percentage rate. That's how much interest you pay every year that you borrow the money for. An APR of 1,500% is the equivalent of around 25% per month. Borrow £100, you have to pay back £125 come payday. How did I find this 25%? I took the 12th route, because there are 12 months in a year, of 15, because that's 1,500% in decimal form, as it were. This gives 1.25. That's because this debt compounds every month to make that 1,500%. More on compound interest in a bit. Basically 1.25 to the power of 12 over a year gives us 15. A mortgage is usually unavoidable if you want to buy a house or other property. It's a huge amount of money a bank might lend you so you can get your dream home, hopefully. You have to pay a deposit, sometimes called a down payment, in essence to prove that you have the ability to make money and pay back the loan eventually. Technically, until you pay back the whole loan, usually after many years, the bank owns the house. That's why if you don't keep up with your monthly repayments, they can repossess your home. You're out of there. This all sounds kind of scary, doesn't it? If so, it might be a bit of a good thing because dealing with loans and credit and debt is something you need to be really careful about. As a rule of thumb, avoid getting into any debt if possible. Sometimes it's unavoidable, like we said, but you must make sure that you have the ability to pay that debt, that loan, back. Interest goes the other way too, though. Have you ever wondered how banks make their money just by holding on to yours? They take the money you've essentially loaned them and they use that to offer loans to other people and businesses. They get a huge amount of interest as a result, and you might see a little bit of that if you're lucky. A normal account, usually called a current account that you can use a debit card for, generally won't give you interest. For that, you'll need to put your money into a savings account. There are all sorts of different ones with different interest rates, usually depending on how easy it is for you to take your money out. Earn too much interest in a year and, you guessed it, the government get to take some of that as tax as well. Similar to loans, interest is given as an annual percentage, but for some reason it's called AER, annual equivalent rate. But again, it's usually paid every month. So let's say you're very lucky and you find a savings account that has a 5% interest rate. By the way, unless it's a fixed rate, this will likely go down over time, but let's assume that it's fixed for a few years here. If you start with £1,000, in a year's time you'll have 5% on top of the 100% you put in, so 105%. So in decimal form, that's times 1.05. So 1,000 times 1.05 is now £1,050. In another year's time, you'll have 1,050 times another 1.05, which is now £1,102.50. Can you see? The interest is getting more and more. This is compound interest. We can say that as a result, your balance is growing exponentially. To calculate how much you'll have over any number of years, take your initial amount, multiply by 1 point whatever the interest rate is in decimal form, to the power of the number of years. So in 8 years' time, how much will you have in your account? Pause the video if you want to have a go first. £1,000 times 1.05 to the power of 8 is £1,477.45. This is why Fry from Futurama was frozen with 93 cents in his account And after 1,000 years when he woke up, his interest rate of 2.25% meant that he had over $4 billion. It turns out that basically the whole of the world's financial systems are based on loans upon loans upon loans, companies getting loans off banks and then those banks getting loans off bigger banks, which is why it's crashed many times in the past. The last big crash being 2008, which was a result of banks lending more and more money that wasn't able to be paid back, often requiring no deposit. They were very irresponsible because they thought there wouldn't be any consequence to their actions. And seeing that governments decided to just make the money they needed out of thin air and bail them out so they could carry on doing the same thing without any other consequences, well, they were kind of right. I'm sure the same thing won't happen again though, right? I hope this has been helpful for you. Money can be scary, but I guarantee you that it gets less scary the more you know about how it works, kind of. So you can enter the big bad world and make sure that you're able to look after yourself and those you love. A prime number is any number that doesn't have any integer factors apart from 1 and itself. Integers is meaning a whole number. That means they can't be divided by any other integer to leave another integer. So that rules out every even number because they all share a factor of 2. That means that they can all be divided by 2 to leave a whole number. That does mean though that 2 is a prime number itself. It's the exception here. So this means we can convert a number that isn't a prime number into a product of smaller prime factors and make this as simple as we can. We can write 6 as a product of 2 and 3. That's just 2 times 3. 4 would be 2 times 2, or 2 squared. 9 would be 3 times 3, 3 squared. 12 would be 2 squared times 3. What would 36 be? Pause the video if you want to have a go. Let's do this one step at a time. 36 is the same as 2 times 18. 18, we can take another 2 out as a factor, so 36 is equal to 2 times 2 times 9. And then we know that 9 is 3 squared. So our final answer is 2 squared times 3 squared. Here's a simple example. What's 2 cubed times 2 to the power of 5? Well, remember that 2 cubed is 2 times itself 3 times. Multiplying that by similarly for 2 to the power of 5, that's the same as multiplying 2 by itself 8 times. So the simplified version of this is 2 to the power of 8. When you multiply the same number with powers on them, you add the powers. If you divide by them, you subtract the powers instead. So 2 to the power of 7 divided by 2 cubed is equal to 2 to the power of 4. Don't forget that if a power is a fraction less than 1, it's a root instead. So 4 to the power of a half is the same as the square root of 4, which is equal to 2. Even with these, you can still add and subtract them. So 2 to the power of a half times 2 to the power of 3 halves gives us 2 to the power of 4 over 2, which is just 2 squared. On the flip side of this, we can multiply or divide numbers with the same power. We say raised to the same power. So 2 squared times 3 squared is the same as 2 times 3 all squared. This follows neatly on to surds. These are the same idea but with roots instead. The square root of 6 is an irrational number. That is, we cannot represent it exactly using a decimal. It would carry on going forever. It's not even recurring. But we can split it into smaller factors though. The square root of 6 is equal to the square root of 2 times 3, which therefore is also equal to the square root of both of these multiplied together. The square root of 15 is equal to the square root, or we sometimes just say root, of 3 times root 5. Root 2, root 3, root 5 are the factors we generally deal with. Splitting such numbers into surds is most useful when using in a bigger formula, as they allow us to express answers exactly rather than a rounded number. The highest common factor for two numbers is found by multiplying the common factors, that is, the prime factors they both have. So what's the highest common factor for 60 and 72? Their prime factors are 2, 2, 3 and 5 and 2, 2, 2, 3 and 3 respectively. So the common factors are 2, 2 and 3. Multiply them together and we get 12. That's our highest common factor. A multiple is the opposite of a factor. 3 is a factor of 18 and 18 is a multiple of 3. To find the lowest common multiple for two numbers, we again take their prime factors and multiply all the factors that appear in either list. So we have 3 2s, 2 3s and a 5. Multiply them together and we get 360. The lowest common multiple of 60 and 72 is 360. Standard form is a way of representing very large or very small numbers more efficiently. This is especially useful in science when considering, say, the mass of the Earth or light years and tiny values like the length of a cell. 10 to the power of 1 is just 10, so 1 times 10 to the power of 1 is also just 10. 10 to the power of 2, however, is 100, so 1 times 10 to the power of 2 is also 100. 1 times 10 to the 3 is 1,000. 2 times 10 to the 3, though, is 2,000. 2 lots of 1,000. What about 4,361? It's more than 4 times 10 to the 3, so we say it's 4.36 times 10 to the 3. Notice I didn't put the 1 on the end. That's because we usually don't give standard form to more than 3 sig figs. That means you have to round to that third sig fig. To turn a number greater than 1 into standard form, we count how many times the usually invisible decimal point has to move to be just after the first sig fig. What would this number be in standard form? Pause the video if you want to have a go. We move the invisible decimal point to just after the first sig fig, so it's moved 1, 2, 3, 4 times. That's our power of 10. So this is 8.37 times 10 to the power of 4. Notice that the 6 was rounded up to a 7 because the next digit was a 5. To convert a smaller number, that's less than 1, into standard form, we have to count how many times the decimal point moves to the right to be after the first sig fig again. Let's say a human cell is measured to be 0.50538 meters long. Let's move the decimal point to after the 5, so 1, 2, 3, 4, 5, 6. That's the power on our 10, but as it's a number smaller than 1, it's a negative power instead. So this is 5.38 times 10 to the minus 6 meters. Again, if the number kept going, we'd have to round to that third sig fig. To put a number as standard form into your calculator, you just punch in the number before the times, then you just press the times 10 to the x button down the bottom. Then finally you put in the power. You don't have to press multiply or put in the 10. This button does all of that for you. You can then do whatever you have to do with it, like any other normal number. However, you might not always have a calculator because we can deal with the power on the 10 like any other power, insofar that we can add or subtract the powers on the 10 if we're multiplying or dividing numbers in standard form. So 3 times 10 to the 2 times 6 times 10 to the 3 is equal to 18. That's just 3 times the 6, and then times 10 to the 5. We've just added the 2 and 3 powers to give us a power of times 10 to the 5. But as we should have only one digit before the decimal point, instead we'd write this as 1.8 times 10 to the 6. We've just moved the decimal place one more. 5 times 10 to the 8 divided by 2 times 10 to the 5, well, that will give us 2.5 times 10 to the 3. We've subtracted the second power on the 10s. If you add or subtract numbers in standard form, they must have the same order of magnitude, another way of saying what power of 10 you have, and that stays unchanged. So what's 3 times 10 to the 5 minus 2 times 10 to the 4? We'd first have to convert one of these to be the same as the other, so changing the times 10 to the 4 to times 10 to the 5 means going up a power of 10, so the number itself must be smaller, so that's now 0.2 times 10 to the 5. So then we can do the calculation. 3 times 10 to the 5 minus 0.2 times 10 to the 5 gives us 2.8 times 10 to the 5. The powers of 10 are unaffected. Algebra is probably my favourite bit of maths because it's used in physics so much. We can use the tools in algebra to literally put planes in the sky, astronauts in space, and much more. It might seem boring on the face of it, but it's OP in the late game, as it were. We can use symbols, including letters, to represent numbers in an expression, we call them. And if that expression is equal to something else, including another expression, then it's now a formula or equation. Let's say we have a term, a variable. We'll just call it A for now, and we have another B. Let's say A happens to be 3 and B is equal to 5. Writing two symbols next to each other means there's an invisible multiplier between them. So AB is the same as A times B. A squared will be equal to 9, as that's 3 times 3. A squared B is 45. That's 3 squared times 5. AB squared is 75, as that's 3 times 5 squared. Careful in these cases, as you might be tempted to say that is 3 times 5, 15, or squared. But if that was the case, you'd have to have brackets around the A and the B, like so. Here's a physics example. Anything that's moving has kinetic energy, so the equation is E, that's the symbol for energy, is equal to half mv squared, where m is the mass in kilograms, v is the speed or velocity in meters per second. So how much kinetic energy does a 0.2 kilogram remote control car moving at 4 meters per second have? A half, or 0.5, times 0.2 times 4 squared. This gives us 1.6. And if you remember your physics, the unit of this is joules, or J for short. When you substitute numbers into an equation or formula like this, always write down the calculation you're doing with numbers in place of the symbols. You can be asked to simplify an expression. Quite often that's useful when you have to use it for another reason later on. For example, the expression 3x squared plus 5x squared plus 10x all divided by 2x. How can this be simplified? Well, we can group together all of the same terms on the top first. So 3x squared plus 5x squared is 8x squared. Don't forget that we write curly x's in maths to avoid confusion with the multiply operator. Now we are dividing by an x, which means that x squared becomes just x, and the x by itself disappears. That's because x divided by x is just 1. That's true for anything divided by itself, isn't it? We've cancelled the x's, we say. We can also divide 8 and 10 nicely by 2, so this ends up being simplified 4x plus 5. What if we have this instead? Multiplying the numbers on top, then the y's, we have 12y squared on top. Dividing by the 3 is easy, that gives us 4. But we now have y squared divided by y cubed. We cancel the y squared from the top and the bottom. It disappears from the top because it's become an invisible times 1, and we're left with just a y on the bottom. Just don't forget that when cancelling something from an equation due to division, it doesn't become 0 but 1. So whatever it was multiplied by stays there. It doesn't disappear itself. Being able to rearrange an equation to make a symbol or term or variable the subject to find its value is crucial. Again, very important in science too. What if we know a runner's energy E and mass m and we want to calculate how fast he's running? Let's rearrange it to make v the subject, to leave it by itself. We have v squared, so we just want to make that the subject first, then deal with the squared at the end. First, let's get rid of the half to the other side. We're multiplying by a half on the right-hand side, which is the same as dividing by 2. So to get rid of it, we multiply the right side of the equation by 2. But whatever we do to one side of an equation, we must do to the other side too. So 2e equals mv squared. The half has disappeared. Next, get rid of the m by dividing both sides by m. M divided by m is 1, so it disappears from the right. It's been cancelled. Finally, we just want v, so we square root both sides. Just swapping the left and the right, we're left with v equals the square root of 2 lots of the energy, 2e, over m, the mass. So if the runner weighs 80 kilograms and he has 2,560 joules of kinetic energy, we just pop the numbers in the place of the variables and his speed turns out to be 8 meters per second. The shortcut for rearranging is this though. To remove something to the other side of an equation, do the opposite with it. So if we're multiplying by something on one side, we divide by it on the other, and vice versa. If something is being added on one side, we subtract it from the other side. Squared on one side, square root on the other, and so on. The quadratic formula allows us to solve an equation that has an unknown value that's squared, say x squared. The equation usually also contains just x's, x terms as well, and just a number by itself to a constant. Let's take this equation here. Each bracket here contains a binomial. That's an expression that contains two different terms. Bi meaning two, nomial, name or term. In this case, as most cases you'll encounter, the two terms are just a linear term, that's just number of x's or y's, etc., not x squareds, and then numbers, so the 3 and the 4 here. You'll be expected to expand, multiply out to such binomials, higher, maybe even 3. We use the mnemonic FOIL to help us remember what to do. That is, every term in one bracket must be multiplied by every term in the other. We multiply the firsts first. 2x times x is 2x squared. We can say that the quadratic coefficient is 2. We have 2x squareds. We started with binomials, but multiplying them out will give more than 2 terms, of course, so it's no longer a binomial. Now the outsides, 2x times minus, or negative 4, is minus 8x. Again, don't get too mad if I say minus instead of negative. Now the insides, 3 times x is 3x. And then finally the lasts, 3 times minus 4 gives minus 12. We now need to group together all like terms. Here it's only the x's we have to do that for. We have minus 5x. By the way, if you're given a binomial squared, you should write them out separately like above and then multiply with FOIL. But in either case, you should be very careful with positives and negatives. If we say that all of this is equal to 0, we can now solve for x, find out what its value is. Actually, I should say values. We know that the square root of 9 is 3, but it's also minus 3. For this reason, x has 2 possible values in a quadratic like this. But they're not just positive and negative versions of the same number because there's more involved. So we say that we have a quadratic coefficient of 2, we have 2x squared. The linear coefficient is minus or negative 5. Finally, the constant is minus 12. We can now use the quadratic formula to solve this. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. A is the quadratic coefficient, b is the linear coefficient, and c is the constant. You will need to do the calculation twice to find both solutions, once with adding and again with subtracting. Popping those into a calculator, we find that x can be 4 and minus 1.5. The The quadratic formula can be used whenever you have expanded equations that contain x squareds, x's, and a unit, even if it's not a result from you multiplying binomials. If you have a formula that has terms on both sides, you must group them together onto one side so everything equals 0 in order to use the quadratic formula. If there's no constant, however, then c is just equal to 0 when you use the formula. If your foundation, by the way, a should always be 1 in the questions you get. These both look like equations, don't they? But there is a subtle yet important difference. The first is an actual equation that has a solution you can solve for x equals whatever. An identity, though, is always true no matter what values are used. For example, 2x plus 6 equals 2 times x plus 3. This is just a statement of a mathematical fact. There's nothing to solve. In essence, you'll find the x's will always cancel. That proves that it's an identity, not a formula. It also means that if you put any number in x's place, you'll get the same value on both sides. This is why we use the triple equal sign. This means is identical to. You can be asked to create a proof to prove something is true. For example, prove that x squared plus x plus 1 is always positive. Well, let's show what's true when x is equal to or greater than 0. The minimum value is 1 and it increases from there. What about for negative values? If it's between 0 and minus 1, then x squared plus x also ends up being between 0 and minus 1, so adding a 1 on the end will always make it positive. Finally, if less than minus 1, then x squared minus x will always be positive, so the whole thing will be 2. So when asked to create this kind of proof, generally you test it with numbers above 1, between 0 and 1, 0 and minus 1, and then below minus 1. What about this one? Prove that the mean of any 4 consecutive even integers is an integer. Consecutive just means one after the other, so 1, 2, 3, 4, 2, 3, 4, 5. This time, we must produce our own expression using x's, whereas the previous one already had it written down for us. We can't just use x, as x can also be an odd number, so we use 2x. That's always going to be an even no matter what value of x you put in there. Incidentally, we represent odd numbers with 2x minus 1. So going back, our first even number in our consecutive line is just 2x. The next number will be 2x plus 2, then 2x plus 4, then 2x plus 6. Finally, any mean is the sum of the values divided by how many there are, so that's adding everything up, 8x plus 12 over 4, which is equal to 2x plus 3. There is no decimal or divide here, showing that this will always be an integer, a whole number, so long as x is an integer. Graphs are also one of those things that might seem naff on the surface, but they're insanely useful. For example, this shows you why nothing happens if you put a metal fork out in the sun, but sparks will fly if you put it in a microwave. A graph is just a picture that allows us to see a function, an equation that involves two variables. Usually y is on the vertical axis, x on the horizontal. They also both go into negative values, so we have 4 quadrants where points can be plotted. The first number is always the x value, then the y. Just put a cross where those two meet. Go across first with the x, down the hall as they say, then up with the y, up the stairs. If the equation is linear, that's just x's and y's involved, there's no power on either of them, you will end up with a straight line graph. Of course, if it's just x or y equals something, you just get a vertical or horizontal line. But let's say we have two coordinates, 1, 3 and 3, 7. Let's plot them. If we join these with a straight line and extrapolate the line, extend it, we have our graph. The equation or function for this line is y equals 2x plus 1. For any value of x we put in there, the equation or function tells us what y will be. What is y equal to when x is 1? That's 3. That's why we have a point there. What about when x is 3? Y is 7. There's a point there too. In fact, if we plotted every point by changing x and seeing what y is, we'd end up with this line. But we only need 2 points in order to draw a straight line graph. The general formula or equation for a straight line or linear graph is y equals mx plus c. We already know what y and x are, but what do m and c represent? M is the gradient or slope of the line. This just tells you how far up the line goes every time you go across 1. So you can find the gradient of any line by making a right angle triangle using the line. It doesn't matter how big it is, the gradient is always the height of the triangle divided by its width. Up divided by across, that's changing y divided by changing x. Let's keep it simple though, I've just made it 1 across. So 2 divided by 1 is 2, so the gradient is 2. That's the m in our equation here. We could have also just used our 2 points we plotted to find the gradient instead. Again, this gives us a gradient of 2. it's constant. Be careful though, if the gradient isn't positive, the line will go down as you go to the right. Technically, in this case, the height of the triangle should be negative to give us that negative value for the gradient. C is the y-intercept. It tells you where the line crosses the y-axis. If this is 0, then the line passes through the origin, 0, 0. Not so here though, we can see that it crosses it at a y value of 1. Again, be careful as the y-intercept could be a negative number. If you have two parallel straight lines, their equations will be different, but their gradients must be the same. That means they'll never meet. If you have two lines that aren't parallel, they must meet at some point. At this point, they have the same values of x and y. That means there is one solution for the two equations. We have simultaneous equations. Two unknowns, x and y, but because we have two equations, we can find a solution. If the two lines are perpendicular, you also know that the gradient is the negative reciprocal of the other. That's because the triangle we would draw for the other one has been rotated 90 degrees, so the height and width have been swapped. It's not 2 over 1, but now 1 over 2. The gradient of this line is a half instead. Well, technically minus a half or negative half, isn't it? Because the slope is in the opposite direction. Non-linear graphs are a bit trickier than linear graphs. It's very difficult to determine what the equation is from looking at values on the graph. Take y equals x squared minus 3, for example. When x is 0, y is minus 3. That's our y-intercept. Fine. When x is 1, y is minus 2. When x is minus 1, y is 2 again. This is a quadratic function, therefore. Any value of y is a result of two possible values of x. Quadratic graphs always have one turning point at the lowest or highest point if it's inverted. Sometimes the turning point won't be at an integer value for x, it could be between two integers. If you're higher, you might have to plot the points by using a table of values that you've calculated, then sketch the curve and you can see where the turning point is or what two numbers it's between anyway. You can also have a cubic graph where the equation involves x cubes. Reciprocal graphs are kind of funky. Take y equals 1 over x. It looks like this. It's two separate curves. For higher, an exponential equation involves something to the power of x. Say y equals 2 to the power of x. It looks like this. It always curves upwards with an increasing gradient. We can also draw a sine curve. It starts at 0, goes up to 1 at 90 degrees, 0 at 180 degrees, minus 1 at 270 degrees, then it starts again at 360. That is if y equals just sine x. If it's y equals 2 sine x, all that means is that the height of this wave goes up to 2 instead of 1. A cos or cosine wave is just a sine wave shifted by 90 degrees, so it starts at 1 instead of 0. A graph of tan x is a weird one. It just increases to infinity at 90 degrees, then appears at the bottom to carry on the function. Just for higher, the equation for a circle takes the form of x squared plus y squared equals a constant squared. This constant is the radius of the circle. If this looks familiar, that's because this is the equation for a right-angled triangle too, which we can draw to show that the hypotenuse is the radius. For higher, you need to know how to find the gradient of the tangent at any point on a circle, the line we can draw to show what the change in gradient is at a particular point. As the hypotenuse of our right-angled triangle is perpendicular to this tangent, we just do what we did earlier. Find the gradient of this hypotenuse, don't forget it could be negative, and the gradient of the tangent will be the negative reciprocal of this. Also for higher, you could be asked to draw a translated functional shape. That just means being moved up or down or left or right by so much. This is done algebraically by saying that whatever y is equal to, that's just a function of x, shorthand f brackets x. We say f of x. This function could be x, x squared, 3 root x, whatever the equation actually is. We're just using this as a shortcut. We're just combining it into this f of x. If we say that a graph drawn is showing the function f of x, again it could be any function, then f of x plus 3 means that every y value is increased by 3. It's being translated upwards. To translate sideways along the x-axis, however, we say it's no longer f of x, but f of x plus 2 doesn't mean it moves to the right, but this time it's translated to the left. A minus would translate it to the right. The reason it's different is because this time, in order for y to be equal to f of x plus 2, that means that every x value has to be 2 less than what it was, hence the move to the left. A reflected function is just the result of sticking a minus in front of the function, or the x. F of minus x is a reflection in the y-axis, while minus f of x is a reflection in the x-axis. Finally, you have to be able to calculate or estimate the area under a graph. This is also used a lot in physics. For example, finding the area under a speed-time graph gives you the total distance travelled. If it consists of straight lines, you can just split the area into triangles and rectangles, etc. Then add up the area of all of these shapes. If it's a curve, however, you need to estimate the area instead. The most accurate way is to count squares, which is a bit of a chore, but to make things easier, you can use double squares, 2 by 2, and count them instead. Count the complete squares first, then count 2 parts of squares that look like they add up to 1. Tally them up and then add them to the total. Then you take that area and multiply by whatever the size of your squares represent. A sequence is a set of numbers, which we call terms, that follow a pattern. An arithmetic sequence is the simplest kind. It's one where the rule is that a number is added or subtracted each time. If that's the same number every time, it's a linear arithmetic sequence. A geometric sequence is one where we multiply or divide by a number each time instead. You could be presented with the start of a sequence and you could be asked to determine what the rule is, or just carry on the sequence, which requires knowing what the rule is anyway. Here the rule is fairly obvious. It's add 3 every time. This is what we call a term-to-term rule. It just tells you how to go from one term to the next. We also have position-to-term rules instead. Basically, the first term in the sequence, we can assign the position 1, the second term has position 2, etc. So if we call the position n, then we can say that for this sequence here, the position-to-term rule is 3n plus 2. Once you have an expression like this for the nth term, you can find any term in the sequence by putting the position in the place of n. So the 10th term would be 32. A triangular sequence is one where we add on the next position to the previous term, and it can be represented by a triangle of dots. First term is 1, second term is 3. The third term, we take our 3 from the previous one and add 3, so that gives us 6. Fourth term, we add 4, that gives us 10. Next term, we add 5, which gives us 15, etc. The nth term is given by n times n plus 1 all over 2. Square and cube number sequences are just n squared and n cubed respectively. A Fibonacci sequence requires you to add the 2 previous terms to get the next one. They might have to deal with quadratic sequences too. Determining the nth term here is pretty tricky. First, find the difference between each term, then find the difference between those differences. This is what we call the second difference. Half of this gives us the coefficient of n squared in the sequence. We then punch in the positions in place of the n's and subtract this from the sequence. This gives us the remainder for each term. This new interim sequence we have will be a linear sequence, which we add to the quadratic part. A ratio is a way of expressing how much of one thing you have to another. Here there are 6 red balls and 3 blue balls. The ratio of red balls to blue balls is therefore 6:3. This can be simplified to 2:1. It's the same ratio. We can also represent a ratio with just a number by dividing the first number by the other. 2 divided by 1 is 2. That means there are twice as many red balls to blue balls. If we wanted the opposite ratio, blue to red, this would be 1:2, or a half. The first way of writing a ratio should ideally just contain integers. We can multiply a number by a ratio to find a proportion of it. So let's say we now have 46 red balls. If the ratio is still the same, how many blue balls is that? We take 46 and multiply by the ratio of red balls to blue balls. 46 multiplied by a half is 23. This ratio is a part-to-part ratio, but sometimes we have to deal with a part-to-whole ratio instead. The initial ratio of 6:3 is 6:9 if rewritten as a part-to-whole ratio. This, of course, can be simplified then to 2/3. Any percentage is just a ratio of how many parts to a whole of 100. Any ratio, usually one that's a fraction, can be turned into a percentage by multiplying the decimal by 100. To find a proportion of something using a percentage, we multiply by the decimal versions. Scale factors are an example of ratios. If you have a blueprint for a house or a map, for example, the scale factor tells you how much smaller it is than the real thing. That means everything on the drawing is 100 times bigger in real life. So if a wall is 1 centimeter long on the drawing, it'll be 100 centimeters or 1 meter long in reality. The gradient of a graph is just a ratio, remember? A gradient of 3 means a ratio of 3:1. We go at 3 every time we go across 1. For a straight line graph through the origin, the ratio is the same all the way up the line. That means that the 2 variables on the axes are directly proportional. If one doubles, so does the other. It's very important in science too. But if things are inversely proportional, that means that when one variable doubles, the other halves, etc. Often it's time on the x-axis, just like for a distance time graph. In this case, the gradient gives you the rate of change of whatever's on the y-axis, somethings per second. The steeper or larger the gradient, the greater the rate of change. Converting units is another example of ratios. I still can't really deal with kilometers, only miles. I'm old school. 5 kilometers I'm going to need that in miles. Turns out that 1 mile is 1.6 kilometers. So the ratio of miles to kilometers is 1 to 1.6, or 1 over 1.6, or 0.625. By the way, this is what we call a compound unit, as it's made from more than one unit. Multiplying that by 5 gives me how many miles I went, and that's 3.125 miles. You can compare ratios involving two different things. For example, price per kilogram of food. I love Lurpak, but every time I go to buy it, I feel like I'm never going to financially recover from it. So is it better to go for the small pack, which is cheaper, or the large pack that's more expensive? On most shop labels now, they tell you how many pounds per kilogram you're spending on your food, which is calculated by just doing price in pounds divided by mass in kilograms. This allows you to compare items and decide which is the best buy. More often than not, buying in bulk, that's just buying bigger packs, means you'll be saving money. Okay, lots of things you need to remember for geometry. Here we go, some definitions or terminology first. A point is just a position on a line, a plane, or anywhere really. A plane is a two-dimensional space on which we can construct shapes. A piece of paper is a horizontal plane, for example, if it's on your desk. A vertex is a corner of a shape where two lines meet. Your phone or computer screen has 4 vertices. An edge can only refer to where two planes meet on a three-dimensional object. Parallel lines are those that point in the same direction as it were, but they will never meet if you extended them infinitely. Perpendicular lines meet in such a way that there is a right angle 90 degrees between them. A polygon is the general term given to any 2D shape, of which there are many. A polygon, a shape, has reflection symmetry if it can be reflected around a line drawn on it. A parallelogram doesn't have reflection symmetry, but it does have rotational symmetry. It looks exactly the same if rotated around its center. The perimeter of a shape is calculated by just adding the length of all its sides. If you're given a funky shape, you might have to infer what the length of some lines are by subtracting a shorter line from a longer line. To draw a perpendicular line that meets another, all you need is a pair of compasses. From here on out, I'm just going to call it a compass. This is useful when you need to find the shortest distance from a point to a line. That's where they meet perpendicularly. To do so from a point to a line, just open your compass a bit more than the shortest distance and draw 2 little arcs on the line. Then put the compass on the points where they meet the line in turn and draw 2 more arcs that should meet on the other side of the line. Then draw the line from this point to the original. To go from a line instead, you do the same, just starting from the line itself this time. A locus is just a line that is made by following a rule relative to a point. Usually that will be a circular path around a point. The rule being that the locus, the line, must always be the same distance from the point. That's the center of the circle in this case. A locus can also be a straight line if you have 2 points that is drawn from, or even an area drawn from a line instead. If you have 2 points, we can draw a locus that is the perpendicular bisector. Bisector just meaning a line that crosses it. All you have to do yet again is use your trusty compass and draw 2 arcs from both points, and the 2 points where they meet will give you the perpendicular bisector if you join them up with a straight line. To avoid confusion when it comes to what direction a line is pointing in, we use bearings. This is an angle that is always measured from north in a clockwise direction. That means that if a plane is flying directly westwards, using a protractor, we can see the angle from north is 90 degrees, but its bearing must be 180 plus the rest to get to west, so that's another 90, so its bearing is 270 degrees. No matter which way a boat or plane or whatever is pointing, bearings are always measured from north. Don't forget that when measuring any angle, the 0 on your protractor must lie on the line you're measuring from. A vector is a line that has a specific length and direction. It shows you how far something has moved and in what direction. It can show you how something's been translated. It can also be represented algebraically by 2 numbers over each other in brackets. The top number is the length of the vector in the x direction, bottom in the y. To translate a point, just add the vector values onto the coordinate. Careful though, there might be negative numbers. To translate a shape with a vector, just apply the translation for each vertex and join up the dots. Adding vectors is as simple as adding the x and y values together. Some will say that you subtract vectors. In reality, you can only ever add vectors. But of course, you might be adding a vector that has negative values, which is the same. A scalar is just a number. It doesn't have direction. So multiplying a vector by a scalar changes both x and y values to make the vector bigger, if the scalar is bigger than 1, of course. To enlarge a shape, just pick a point away from the shape to be the center of enlargement, then join this to every vertex of the shape with straight lines. Measure the length of these lines, then continue them, making them as many times longer as the scale factor. So if you want to make this triangle 3 times bigger and this line is 1 centimeter long, extend it so it's 3 centimeters long. So if the scale factor is 0.5, go halfway to each point. That's where you're going to draw your points and then join them together to make your smaller shape. For higher, you could have a negative scale factor. In this case, you extend the lines back the other way and continue similarly to normal. Before we look at individual shapes, it's worth knowing the rules about angles and lines. The angles between lines around a point always add up to 360 degrees. So what would this unknown angle be? We do 360 minus the known angles and boom, we have the one remaining angle. When a line meets another, the two angles must add up to 180 degrees. Similarly, if there's more than one line. Of course, if they meet perpendicularly, the two angles are 90 degrees each. If one line crosses another, intersects it, we have the same angles on both sides, just flipped, or rotated anyway. We now have corresponding angles. The angles opposite each other around the point are equal. If a line intersects two parallel lines, all of these angles are actually just two lots of corresponding angles, as you can see here. Triangles are very important. In fact, any video game that isn't 2D is a result of millions of tiny triangles being calculated every second to produce the image you see on the screen. Any polygon can be split into a number of triangles. Any four-sided shape, a quadrilateral, is made of 2 triangles. A 5-sided shape, a pentagon, can be split into 3 triangles, etc. Add up all the angles in all the triangles you've split it into, and you found the sum of angles in your polygon. The other polygon names you need to know are hexagon, 6 sides, octagon, 8 sides, and decagon, 10 sides. There are 3 special triangles. All 3 of an equilateral triangle's sides, lengths, and angles are equal. As angles in a triangle must add up to 180 degrees, that must mean each angle must be 60 degrees in this case. It has 3 axes of reflection symmetry and 3 lots of rotational symmetry. An isosceles triangle is one that has 2 identical angles, and therefore 2 sides of equal length too. As such, it has reflection symmetry around one axis. If the length of the sides of a shape are equal, we can put a little line through both of them to show this. If there's another pair of lines that are also equal to each other, say in a rectangle, we can use 2 little lines to show this. We can also use these ticks on angles if they're the same too, or use double curves instead. A right angle triangle has, you guessed it, a right angle in. More on what we can do with these in a bit. Any other triangle that isn't one of these special ones is called a scalene triangle. If all 3 of the angles are less than 90 degrees, we call it an acute angle triangle. If it's got one angle that's greater than 90 degrees, it's an obtuse angle triangle instead. The area of any triangle can be calculated by multiplying the length of one side by the perpendicular distance to the opposite vertex and halving this. However, if you can't measure this perpendicular distance, fear not, as there's another way. Half AB sine C, where big C here is the angle between the sides A and B. You can choose which is which. We use little ABC for the sides and capital ABC for the angles opposite them. We also have the sine and cosine rules that work for any triangles, but we don't use them with right angle triangles. The sine rule is this: A over sine A equals B over sine B equals C over sine C. In other words, any side over the sine of its opposite angle will give you the same value no matter which you choose. Say we're just concerned with sides A and C, we just take out B, and then we can just rearrange to find an unknown. Don't forget that if you end up with sine, cos or tan of an angle equals something, but you need to find the angle itself, you do inverse sine, cos or tan of the other side of the equation. That's shift, then sine, cos, tan on your calculator. Similarly, the cosine rule also works for any triangle. C squared equals A squared plus B squared minus 2AB cos big C, where the C on the end is the angle opposite side C. You can choose which is which, of course, unless the triangle's already labelled. In this case, just change the little ABCs around, just making sure that the angle after the cos is the angle opposite the side you have before the equal sign. There's a lot we can do with right angle triangles. They're used a lot in physics too. We can use Pythagoras' theorem to find the length of the hypotenuse, the long side. We call the hypotenuse C and the other 2 sides A and B. It turns out that A squared plus B squared equals C squared, or C equals the square root of A squared plus B squared. If you're asked to find one of the shorter sides, you must rearrange this. Trigonometry, or trig, is the area of math that lets you find the sides of a triangle from its angles or vice versa. If you know the length of one side and one of the 2 angles that aren't the right angle, you can find out everything else. Let's say we know this angle here. The longest side is always the hypotenuse, but then we must label the other 2 sides. The other side it touches we call the adjacent, A, and the one on the other side of the triangle is the opposite side. We just call it the opposite, O. We can then use our mnemonic SOHCAHTOA. That is sine theta, theta just being the angle that we're looking at, equals opposite over hypotenuse. Cos theta equals adjacent over hypotenuse. Tan theta equals opposite over adjacent. You just choose the one that has the two things you know in. So let's say we know the angle and the hypotenuse, and we want to find the length of the opposite side. Which out of SOHCAHTOA do we choose? It's the SO. Sine theta equals opposite over hypotenuse. We want to find the opposite, so move the h to the other side by multiplying the other side by it. If we were being asked to find an unknown angle here using SO, then we do inverse sine of opposite over hypotenuse. That gives us the angle theta. Unfortunately, you have to remember some values for commonly used angles, so you could be expected to do trig or sine and cos rules without a calculator. Rubbish, eh? Here they are. Most of the time it will be sine or cos of 0, or sine 30 and cos 30 being a half, so make these a priority. We can say triangles are congruent when they are the same. Their sides and angles are the same. But you don't need to know all three angles and sides to know if they're congruent. You only need to know 3 out of these 6 things. If the length of all 3 sides of 2 triangles are equal, they must be the same. We say that this is SSS congruence. SAS is side angle side, where 2 sides and the angle between them are the same for both triangles. Again, that must mean that they're congruent. Flip side of this is ASA. That's angle side angle. And RHS is right angle hypotenuse side. This is only true for right angle triangles, of course. When written in a question, angles are given by 3 letters representing the corners. And again, we use capital letters for these. The middle letter being the point or vertex where the angle is that we're considering. Quadrilaterals are polygons with 4 sides. Quad 4, lateral side. Both squares and rectangles consist of 2 lots of parallel lines that are perpendicular to each other. As such, they have 4 right angles. The angles add up to 360 degrees, just like every quadrilateral. This is because they can be split into 2 triangles, like we've said, each containing 180 degrees. To calculate the area of a square or rectangle, just multiply 2 adjoining sides. A parallelogram also has 2 lots of parallel sides, but no right angles. It's a skewed rectangle. The area of this is calculated by multiplying the length of one side by the line perpendicular from it to the opposite side. In other words, the base width times height. 2 adjacent angles in these always add up to 180 degrees. A rhombus is a parallelogram where all sides are the same length. You can use the previous formula for its area, but you can also draw a cross joining the corners. Half times the length of one, then times the other, gives you the area. A trapezium or trapezoid only has 1 pair of parallel lines. The other 2 aren't parallel. The area is given by the average length of the parallel sides, so half their sum, multiplied by the height. Finally, a kite is a kite. It has 2 pairs of lines of equal length that are joined to each other. We can use the cross formula from the rhombus here again to find the area. A few terms specific to circles. Radius is the distance from the center of the circle to the line. Diameter is double this. Circumference is the perimeter of the circle, equal to 2 pi r or pi d. The area of a circle is equal to pi r squared. A tangent is a straight line that just touches the outside of the circle at one point. This will always be perpendicular to the radius at that point. An arc is a portion of the circumference between 2 points on the circle. A chord is the straight line between 2 points. A segment is the area enclosed by an arc and a chord, whereas a sector is a piece of the pie, as it were, the area enclosed by 2 radii and an arc. The length of an arc can be calculated from the angle given. This angle will be a proportion of 360 degrees, so just find this ratio, then multiply by the total circumference. To find the area of a sector, just multiply by the total area instead. For higher, you need to know that an angle in a shape is subtended by the opposite side, so in this case, the arc. There are a few rules you need to remember. The first circle theorem, the angle subtended by an arc at the center is twice the angle subtended at the circumference. In essence, the angle is double at the center compared to when it's at the line. This is true no matter where the angle on the line is, so long as its 2 chords meet at the 2 radii lines from the center. The proof is this: split the angle with the diameter and call the 2 separate angles x and y. We now have 2 isosceles triangles. As such, the other angles at the edge are x and y too. The angles at the center therefore must be 180 minus 2x and 180 minus 2y. The angles outside the triangles must be 2x and 2y, bringing the total angle to double the original. Next, the angles subtended by the same arc must be equal. This follows on from the first theorem. If we join the common points to the centre, we know that the angle subtended there must be double that at the line, no matter where the far point of the segment is. A cyclic or cyclic quadrilateral is a four-sided polygon where all four vertices or corners touch the line, the circumference. Two opposite angles in one of these always add up to 180 degrees. The proof? Join two opposite points to the centre and say the other angles are x and y. The angles on the other side must be double these, so we have 2x plus 2y around the centre in the circle, which must add up to 360 degrees. So halving this, x plus y equals 180 degrees. If we make an arc a semicircle, the other point's angle will always be 90 degrees, and it will always be a right-angled triangle. Why? Employing the first circle theorem again, the angle subtended at the centre must be 180 degrees as it's a straight line, which must be double the angle at the circumference. When two tangents are drawn from points on the circumference to the place where they meet, they must be equal in length. This one might seem a bit more obvious, but we still need to be able to prove it. This is true just because if we draw the two radii, they must be perpendicular to the tangents, and the angles within the two triangles must also be equal, so the lengths of the sides are 2. If you have a chord and draw a line to the centre of the chord, they will be perpendicular. This is merely because we now have two identical but reflected right-angled triangles, meaning the lengths must be equal. And finally, the alternate segment theorem. The angle between a tangent and a chord is equal to the angle in the alternate segment. This proof might be the hardest, so here we go. As per usual, we join 2 points to the centre by drawing radii, and we've made an isosceles triangle. And we can see that we have two lots of 90 minus x. That means the final angle must be 2x, and going back to our first theorem once again, the angle on the other side of the circle must also be x. So that just goes to show how important the first circle theorem is. If you can't remember all of these proofs exactly, just remember to A. Join points at the centre to make isosceles triangles, and they will have two equal angles, and that angles in a triangle add up to 180 degrees, and B. Use the whole double angle theorem to find the angle at the circumference. A prism is any 3D shape that has a constant cross-section. A cuboid is a square or rectangle all the way through. A cylinder has a circular cross-section. To find the volume, we calculate the cross-sectional area, or CSA for short, like we did for the 2D shapes, then multiply by the height of the prism. To find the surface area of a cuboid, just add up the area of all 6 faces. The volume of a sphere is 4/3 pi r cubed, while its surface area is 4 pi r squared. A pyramid is any shape where all edges meet at a point. The volume is equal to 1/3 times the area of the base times the perpendicular height, or the vertical height. To find the surface area, find the area of one face, which is a triangle, then times by the number of faces, and don't forget to add on the area of the base too. The volume of a cone is 1/3 pi r squared times its vertical height, while its surface area is the circular base pi r squared plus pi rl, where l is the length of the cone from bottom to top. Again, that's not the vertical or perpendicular height. Probability is the chance of something being true. Basically, we're using ratios again. For example, put your hand into a bag with 5 blue balls and 5 red balls and pull one out without looking. There's an equal chance you'll pull out a red or a blue. You might say there's a 50-50 chance. We say this because there's a 50% chance of either outcome happening. Like any ratio, probabilities can be given as a fraction, decimal, or percentage between 0 and 1, but it's always given as a part-to-whole ratio. We also calculate probability by dividing the desired outcomes by the total number of outcomes. So let's say we now have 8 blue balls and 2 red balls. What's the probability that you'll pick out a blue ball? The part, 8, divided by the whole, 10, gives 0.8, multiplied by 100, and that's an 80% chance of this happening. That's fairly probable or likely, we can say. What's the probability that you won't pick a blue ball? It's just 1 minus the other, so 1 minus 0.8 is 0.2, or 100% minus 80% is 20%. This is only true if each event has the same probability. It's unbiased. If you got to look at what balls you're picking, this would no longer be unbiased. This would now be biased. In these kind of cases, you must be given the probability of an outcome happening, usually in a table. If there's a probability missing, you know you can find it by doing 1 minus the rest, leaving you with the remaining unknown probability. If there's only blue balls in the bag, the probability of you picking one is 1, or 100%. It's certain. Just red balls though, and that probability drops to 0, or 0%. There's no chance you'll pick out a blue ball. It's now impossible. Let's say you take out a ball at random, see what color it is, put it back and repeat this, say, 50 times. What should be the frequency that you pulled out a blue ball? That is, how many times it happens. You should have pulled out 40 blue balls, and therefore 10 would be red. Will that happen in reality? Maybe, but maybe not. Let's say you pulled out 35 blue balls. That means the relative frequency in this real world test was 35 divided by 50, 0.7 or 70%. But the more times you repeat these kind of tests, the closer this relative ratio frequency will get to the calculated theoretical probability. We say that if the sample size is larger, then the relative frequency will tend towards the theoretical probability distributions. To tend just means to get closer to, distribution just means how the outcomes are spread. To find the probability of two different events happening, for example, what is the probability of a person chosen at random being a bloke and having blonde hair, we can use a tree diagram for this. Men and women are roughly 50-50. The probability of someone having blonde hair varies with country, but let's say that it's 40%. 40% of all people in the UK have blonde hair. To find the probability of two independent outcomes being true, that's outcome 1 and outcome 2 being true, we multiply the probabilities in decimal form. So 0.5 times 0.4 is 0.2. There's a 20% chance of a randomer being a blonde dude. A tree diagram can also be used in the other way. That is, we can just count the frequency of different outcomes by just, getting people and counting them and putting those numbers on the end of each branch. A sample space diagram is slightly different, as this shows you what the possible outcomes are for two events that involve numbers. For example, the rolling of two dice and adding them up. We can see there are 36 possible ways they can be rolled, all with equal probability. As there's only one way you can roll a 12 though, the probability of this happening is 1 over 36. The probability of you rolling a 9, however, is 4 over 36, as there are 4 different ways that this can happen. Simplifying, that's the probability of 1/9. Just for hire, going back to our bag of balls, if you pick one, then put it back, then it will not affect the probability of what ball you pick next. We say the events are independent. One doesn't affect the other. Keep it out and pick another, however, and this is no longer true. The two picks are no longer independent, but they are dependent. We still multiply the two probabilities, but the next probability will now be different. So pick a blue ball, the probability is 8/10. But what's the probability you'll pick one now if you've picked one out? It's not 8, as there's only 7 blue balls left and only 9 balls altogether, so the probability now is 7/9. So what's the probability of you picking 2 balls in a row? 8/10 times 7/9. That gives us 56 over 90. Simplifying, that's 28 over 45, or 0.62 as a decimal, 62%. Venn diagrams. There's no scale here, it's just a way of us visualizing frequencies of data we've obtained. Let's say we asked 100 people if they like tea and or coffee. We make 2 circles, they're likely to overlap as there will be people who like both. If not, then we only have 2 separate circles, which kind of defeats the whole purpose of Venn diagrams, but it is possible. Let's say 50 out of that 100 like both beverages. We put that in the space where the 2 circles overlap. 30 only like tea, so they go in the left circle, and 5 people only like coffee, weirdos. They go on the right, but that only accounts for 85 people. Who are the other 15? They're the ones who don't go in either of the circles. They go on the outside where they belong. But still in a box, we put around everything to show that we've accounted for everybody. The squiggly E is a Greek letter zeta. Don't ask me why we use it, but we do. This is just to show that we have the universal set. It just means we haven't left anyone out. Statistics follows nicely on from probability. It's essentially probabilities on a large scale. We collect data from the real world, then analyze it. If data is said to be discrete, this means that it doesn't continually change. For example, eye color. Yes, there might be a spectrum in reality, but we might say that values are blue, brown, and green, for example. If it's not discrete, it's continuous. This data does continually change, like people's heights, say. Primary data is data that's been collected directly from the source. For example, you going out and asking people if they like tea or coffee. If someone else found the data instead, and you took that data to analyze, this is now secondary data. We draw a table with the values in the first column, then tally, which is a quick way of counting. Then after we've done that, we turn that into an actual number for the frequency at the end. We can use two-way tables if we have 2 variables, like hair color and eye color. Population refers to the total number of people we apply our data to. We found that 20% of people liked tea but not coffee earlier from a sample size of only 100 people. As there are 67 million people in the UK, that suggests that 67 times 0.2, 13.4 million people just like tea but not coffee. However, like we said earlier, the greater the sample size, the more accurate these calculated probabilities are. So why not just ask 67 million people? Well, that would take too much time, effort and money. So there's always a trade-off between getting accurate data and being cost effective. A chart or graph is just a way of representing data in a way that makes it easier for us to analyze. Bar charts are used for discrete data. We put frequency up the y-axis. It should start at 0, but some dishonest people out there in the big bad world won't do this in order to make differences seem larger than they are. Very naughty. You can show two variables on a bar chart by splitting the bars into different parts too. So you could have the number of males and females with certain hair colors on top of each other, so you can see the individual frequency for hair color for males and females and the totals too. A line chart is the same as a bar chart, it just uses lines. Very similar, just harder to read, so goodness knows why you'd use those. Pictograms are the Fisher-Price toy of charts, if you will, essentially a bar chart that uses pictures instead of bars. Most bizarre and very tabloid newspapery. Pie charts just use sections of a circle to represent discrete data, but we must have relative numbers or frequency here, then multiply by 360 degrees to calculate the angle of each segment. So if 40% of people have blonde hair, we do 0.4 times 360, which is 144 degrees. A histogram is a kind of bar chart that shows continuous data, so the bars touch. They're especially useful when dealing with group data that has an unequal class interval. Say that we have people aged 11 to 20, which includes 10 different ages, then so many people aged 21 to 40 years. The second interval is larger with 20 different ages. We can't just draw the raw frequencies on the histogram, as that wouldn't show us anything. Instead, we must draw the frequency density for each group or interval instead. Take the frequency for an interval, then divide by the range of values in that interval. So 20 divided by 10 gives us a frequency density of 2. We plot that for the first group. Then 60 divided by 20 for the second age group gives us a frequency density of 3. So we plot that spanning that interval. Scatter graphs are incredibly powerful. They reveal a lot about the world and are used in science all the time, as you probably know. We use these for bivariate data, that's continuous. Bivariate just means that we have two variables that are changing, one on each axis, and the graph shows us what correlation there is between them, if any. We can draw a line of best fit to make this relationship clearer. If both variables increase, the line of best fit will have a positive gradient, a positive correlation. However, if one decreases while the other increases, we have a negative gradient, a negative correlation. If the points are all over the shop, there might be no correlation at all. Using a line of best fit, we can interpolate to estimate where a point might be between actual points. We can also extrapolate by extending the line past the points that we do have to do the same. Interpolating is considered to be far more accurate than extrapolating, as a small change in the gradient of the line of best fit will change where the point is if you extrapolate a lot. That means that it's not very accurate if you do it far away from the data you do have. There's a big problem with scatter graphs though. We might see a correlation and say, oh, the increase in X definitely caused the increase in Y. However, there might actually be no causation whatsoever. It could just be a coincidence that there is a correlation. Correlation does not necessarily mean causation. The other issue is that it might be the other way around. It's the increase in Y that actually caused the increase in X. Both of these issues are causing big problems in science and society these days. People interpreting graphs incorrectly, sometimes intentionally to suit their own goals, which in turn causes huge issues, which in turn can cause national or global leaders to make very bad decisions. There are two more charts you need to know for hire. A cumulative frequency graph shows how the total frequency changes, so in essence it shows the frequency of all values below that one. As such, it can be used to show continuous data, but only if grouped into equal intervals. For normal statistics, this line will curve upwards at the start, then level out at the top, as we have smaller frequencies at the two extremes of data usually. We often split this data into quartiles, going from 0 up to a quarter of the total frequency. We can find at what value a quarter of the sample group are below. This is the lower quartile. Doing the same at 3/4 of the total frequency gives us the upper quartile. Doing half gives us the median value. More on this in a minute. A box plot is essentially a bar chart version of a cumulative frequency graph. We have a line going from the lowest value to the highest, sometimes called the whiskers, and a box that goes from the lower to upper quartile, and a line in the middle to show the median. The difference between the lower and upper quartiles is called the interquartile range. Finding an average is incredibly useful for all sorts of reasons, but there are different types of average. More often than not, in other subjects like science and in wider life, average usually means the mean. This is calculated by adding up all values and dividing by the number of values. For example, if we measure the mass of 5 ball bearings, but they're all slightly different, we can find the mean by adding up all the masses and dividing by 5. The mean value should always be to the same number of significant figures as the values themselves. It is possible that they'll try to catch you out by throwing in an outlier, an anomaly in the mix. If there's a value that looks very far off the rest, then you should omit it, leave it out of the calculation for the mean. The range or spread of values is just the maximum value minus the minimum value. Highest take away lowest. Careful, that doesn't necessarily mean that's the first and last values when they're listed. Again, if there's an outlier, ignore it in the range calculation too. If you're asked to find the mean from a frequency table, you must multiply the frequency by the values, then divide by the total number in the sample. The median is just the number in the middle of a set of data. So if you have 5 values that are listed from smallest to largest, then the median is going to be the third value. If you have an even number of values, there will be 2 values in the middle. In these cases, we give the median as the number halfway between these 2 values. The mode is the value that is most common in a set of data, the one with the highest frequency. So in our 5 ball bearings, we have a value that crops up twice, so that's our mode. There could be 2 modes or even no mode if all values are different. If it's group data you have, then the mode is technically now called the modal group or modal class. So I hope you found this helpful. Leave a like if you did. Don't forget to check out the channel for science revision videos too. See you next time.